This video is going to mark the start of our look into vibrations. So vibrations are common pretty much in any machine or mechanical system where we have some sort of motion occurring. And vibrations are important to consider from a machine or a structural standpoint because vibration means that the members of that machine, that the components, the members of the structure, are seeing cyclic loading. And cyclic loading leads to fatigue, which is usually the mechanism by which something will fail. So from that perspective, vibrations is a pretty important topic to consider when we talk about engineering applications. So to start with for vibrations, we're going to start with probably the simplest form, which is that we have a spring, and on the other end of that spring is a mass hanging from it. And the type of motion that we would expect to see if we were to disturb that mass is called undamped free vibration. So undamped meaning that there's nothing slowing it down in particular. Of course, we're talking about an idealized case here where there's no loss due to deformation and of the material and things like that. And also it's free vibration, which means we're not driving the motion. We're not continually moving the mass up and down with some sort of external force. So that's the version of this that we're going to look at. So if we look at this mass and it's hanging from the spring in just kind of a free state, meaning it's in equilibrium, it's just hanging there. In equilibrium, we would draw or could draw a free body diagram of this mass and say that we have the weight acting down on it, and then we have the force of the spring pulling back. Now the force of the spring in this case is equal to the spring stiffness multiplied by the deflection. And the deflection is measured relative to some unstretched orientation of the spring. So for example, over here, if I drew my mass attached to the spring again, but now we lifted the mass up so that the spring is unstretched, meaning it's in whatever orientation it would have if we didn't apply any mass or any load to it at all, then this deflection is measured relative to that. We've stretched the spring now by applying some mass to it and obtaining some deflection here. So in this scenario, we have an equilibrium condition. So again, the mass is just resting here. And in equilibrium, then we could say that W equals K delta. Now, the next question then is what would happen if we stretched or pulled that mass down a little further? So now I'm going to pull the mass down a little bit further from this equilibrium condition. So now the position I'm measuring here, I'll call X, and it's how far I've stretched the spring or moved the mass down from its equilibrium position. So now if once again we draw a free body diagram, I would say that we have the weight acting on it, and we have the force of the spring pulling back. Now the weight, recall, hasn't changed, and here we said it was equal to K delta, and we're not changing any of the definitions of delta or anything like that, so therefore we can still say that the weight is equal to K delta. Now the force of the spring is still resulting from the spring stiffness K, but now the deflection that it's seeing is delta plus whatever new position we've moved this to, X. So we have an equation that looks like this. So now if we go ahead and write a summation of forces in the X direction, again X is directed positively downward as I've shown it here, then I have W minus Fs, which we just said was equal to k delta for W minus k delta plus x. And we can see from this that if we distribute the k through, we get a minus k delta and a minus kx. The k delta here is going to cancel with the minus k delta, and we're left with minus kx. So this force is a restorative force. It's the force of the spring trying to bring this system back into equilibrium. And therefore it's always going to be directed in the direction of equilibrium. So wherever the default equilibrium state of my spring is, that's the direction that that force is going to be applied. So now let's think about this from a equilibrium equation, or from a equation of motion, I should say, and say that the sum of forces must equal ma, which we know is our standard equation. So I just up here said that the sum of forces is equal to k delta. So I'm going to say, or excuse me, minus, sorry, not k delta, minus kx. And I'm going to set that equal to mass times acceleration. Now, recall, for our notation purposes, we can rewrite this acceleration as x double dot. So double dot indicating it's the second time derivative of the position x. So this gives us a form of the equation that looks like this. mx double dot plus kx equals 0. Now, if you've ever seen this expression before, or done anything with vibrations before, this is starting to look familiar. This equation is a simple differential equation which allows us to evaluate the position x with respect to everything else that's going on. And we'll take that a little bit further in the next video. All right, thank you.